All right, in this video, we're going to talk about angles and the measurement of angles. So, an angle is made with two rays from the same endpoint called a vertex. One of the rays we're going to call the initial ray, and the other ray is we're going to call the terminal ray. So we have two rays from the same endpoint. One is our initial ray, and one is the terminal ray. Now, the measurement of an angle is the amount of rotation needed to go from the initial ray to the terminal ray. So if we're looking at this being our initial ray and this being our terminal ray, how much did I have to rotate to get from here to here? Now, just as a side note, a lot of times with angles, we will symbolize them with Greek letters. Theta, phi, alpha, beta, and gamma are all pretty common angle measurements. Probably the most common one in this class is theta. But when we deal with triangles, we'll use alpha, beta, and gamma a lot as well. If you get into some other classes, you may see the angle phi, and you can write phi in two different ways. Circle with a slash through it, or this kind of looks like you're trying to make a circle and then you make a slash down. It's almost like a cursive circle with a slash through it. Theta looks like a zero with a little line across, or sometimes that line will arch across. But these are all different variables for our angle or for our measurement of the angle. So if we're measuring rotation, how do we want to measure rotation? There's actually two different ways we can measure rotation. One is in degrees and the other is in radians. Now, what we do if we're measuring in degrees is we start out by defining that a full circular rotation is 360 degrees. With radians, we say a full circular rotation is 2 pi radians. Let me explain what I mean by full circular rotation. So what I've done is I've graphed two rays on Desmos. Now, standard starting position we'll see on the next slide is the ray going out from the origin along the x-axis. If I want to do a full circular rotation, what I do is I take the other ray and I start to rotate that all the way around until I get all the way around one full circle. So that would be a full circular rotation where my initial ray circles all the way around until my terminal ray gets moved all the way around until it touches the initial ray here. That's what we mean by full circular rotation. In degrees, that's a 360-degree rotation. In radians, that is a 2 pi rotation. And if we know that, then it's pretty clear that if you do a half of a rotation, if you do a straight line here, this is not perfectly straight, but if you do a straight line here, then that would be a half of 360, so that would be 180 degrees. And that would be half of 2 pi, which would be pi radians. If I did a quarter of a rotation around, again, this is not a perfect situation there, but there. A quarter, well, a quarter of 360 would be 90 degrees, and a quarter of 2 pi would be pi over 2 radians. So all of my other degree measurements and radian measurements are based off of what percentage of the circle did I rotate around. Now, like I said, the standard position of the initial ray is pointing right along the x-axis and starting at the origin. So we start at the origin, point right along the x-axis. That's the usual standard position for the initial ray. And then the terminal ray gets moved based off of how many degrees or radians it is away. And when I started doing that example, that visual earlier on Desmos, I was rotating the ray in a counterclockwise fashion. Counterclockwise rotation means we have positive angle measurements. On the other hand, if I would have rotated my terminal side in a clockwise manner from my initial ray, then I would have had negative angle measurements. So positive measurements happen when rotation is counterclockwise, like I was doing, and negative measurements happen when rotation is clockwise. Now, 2 pi should look familiar. 2 pi is actually the ratio between the circumference of a circle and the radius of a circle. In other words, the circumference of a circle is 2 pi times the radius. And if you think about what that means, why is a full rotation in radian measure equal to 2 pi? It's because of its connection to arc length. So because the entire circle has circumference of 2 pi over r, the arc length of any portion of the circle is going to be connected to radians. Let me explain what I mean by that. So here what I've done is I've graphed the circle, and this one is a radius 1, and the arc length is the portion of that circle within the initial versus terminal ray. So the portion of that circle, that's the arc length of the circle, that's connected to radians. If I go all the way out to 2 pi, the length that we've traveled around that circle is the same as the 2 pi radians times the radius of that circle. Now, in this case, our circle happens to be radius 1, so it's 2 pi radians. And if I wanted to find the arc length of a quarter of the circle, what I could do is I could say, well, the angle that I'm making here is pi over 2 radians. So the arc length is going to be pi over 2 times the radius, in this case 1. So that arc length is pi over 2. And if I wanted to do some other value, if I wanted to find this arc length, it would just be the radian measure of the angle times the radius of the circle. So arc length is connected in a very straightforward way to the radian measurement of our angle. Now, because we have two different ways of measuring angles, we're going to want an easy way to do a conversion between degree measurement and radian measurement of angles. So if I know the angle is 13 degrees, how many radians is that? Or if I know that it is 1.2 radians. How many degrees is that? The way we do conversions, or at least the way I do conversions, is I just multiply times a fraction of 1. So a fraction of size 1. And we can create a fraction of size 1 by noticing that 360 degrees is the same measurement as 2 pi radians. So 2 pi radians divided by 360 degrees, or 360 degrees divided by 2 pi radians, will be a fraction of 1. Now, oftentimes we don't use that one because of the coefficient of 2 here. Oftentimes, instead of using 360 is equal to 2 pi, we use 180 degrees is equal to pi radians. That way I don't deal with the coefficient of 2 there. So most times people use this identity in order to do conversions. So let's go ahead and do that for a few examples. In this example, we're going to convert degrees to radians. I'll show you how it's done on the first one, and then I'll push pause, or you can push pause on the video and try it if you'd like. So let's convert the following angles from degree measurements to radian measurements. 42 degrees, 217 degrees, negative 51 degrees, and 324 degrees. So like I said, what we're going to do is we are going to multiply times a fraction that's equal to 1. And since my label of 42 degrees is in degrees, I'm going to have to put the degree label in the denominator. Now we know that 180 degrees is the same thing as pi radians. Again, you can utilize 2 pi over 360 as well, but most of the time people use pi over 180, pi radians as 180 degrees. Since we're multiplying, since pi radians and 180 degrees is the same, we're multiplying by a fraction of size 1. But also, because we have degrees here and degrees here, one is in a numerator, one is in a denominator. So those labels will cancel each other out, and whatever I get out will be in radians. So multiply 42 times pi, that will go in the numerator, and then 180 will go in the denominator, and our label will be radians. So 42 degrees is 42 times pi over 180. Now 42 over 180 can be simplified. That simplifies to 7 over 30. So our angle we could write as 7 pi over 30 as well as radians if we wanted to. That's the exact angle in radians. Now, it's also true that you could write an approximate value for this as well. That's about 0.7330 radians if I just plug in 7 times pi over 30. I won't write that for this one, but you can also get a decimal approximation of this fraction if you'd like. And we can do all of these conversions in the exact same way. I'll give you an opportunity to pause the video and try the other 3 conversions on your own. And then in a couple of seconds, I'll show you how they're all done. All right, so let's go ahead and do all of these. So we're going to do them in the exact same way. I don't have to always write all the labels. A lot of times people will just write pi over 180 and they know that they are canceling things out. I will, in this case, just say times pi over 180 degrees. And that's going to be 217 pi divided by 180. 217 pi over 180 does not simplify in a nice way as a fraction, but we can, if I wanted to, get an approximate decimal of about 3.7874 if I round it to 4 decimal places, radians. Okay. So whichever way, if you want the exact answer, it's 217 pi over 180. If you want an approximate answer, it's about 3.7874. And that's rounded to 4 decimal places. Obviously, if you rounded to 2 decimal places, we'd be 3.79. If I take negative 51 degrees and convert it, again, I'm going to multiply by pi over 180. And what that is, negative 51 over 180 does simplify to 17 over 60. So if I wanted to use the simplified version, it'd be negative 17 pi over 60. This is, again, if you wanted to use a decimal version of that, that's okay too. That's about negative 0.89. I'll just round this one to a couple of decimal places. So negative 17 pi over 60 is the exact answer. Negative 0.89 is the rounded answer. Now let's take 324 degrees, multiply that by the fraction of size 1. Again, we're using pi over 180. That is pi over 180 degrees. And when we simplify that, that's 9 pi over 5 radians. I'll just leave the exact answer up there. You can convert that to a decimal if you'd like. So there you go. Converting from degrees to radians is just the same thing as multiplying by a fraction of size 1, whose label on the numerator is in radians, and in the denominator, the label is in degrees. I use pi over 180, but you could also have used 2 pi over 360 and got the exact same values. Now, in the exact same way, but with the reverse fraction, we can convert from radians to degrees. Knowing that 180 degrees is pi radians, we can convert from radians to degrees. So if you want to, try these on your own. Try converting each one of these angles, which is measured in radians, into an angle measured in degrees. I'll give a couple of seconds for you to do that, and then I'll show you how to do these four after I give you a couple seconds. All right, so we have pi over 5 radians, and we're going to multiply that times a fraction of size 1. This time, because we want to cancel out the radian label, I'm going to put pi radians in the denominator. Let me put a space there. And 180 degrees in the numerator. If I do that, then what happens, interestingly enough, is because we have pi here and pi here, the pi's will cancel each other out, and 180 divided by 5 becomes 36 degrees. So pi over 5 radians is actually the same as 36 degrees. I won't write the labels each time, or at least not all of the labels, but we're going to do the exact same thing in all of the other three. So we're going to multiply times a fraction. Again, numerator of that fraction is going to be 180 degrees. Denominator is going to be pi radians. When you do this multiplication, what you get is 300 degrees. So 5 pi over 3 radians is the same thing as 300 degrees. Let's take negative pi over 10. Again, multiply that times the fraction of 180 degrees divided by pi radians. I'm leaving off the word radians just for the sake of time. And what that is negative 18 degrees. So negative 18 degrees is the same thing as negative pi over 10 radians. These three came out to nice integer values in degrees because they are all involved pi. But when we have something that doesn't involve pi, like 1.78, then when we multiply that times 180 degrees over pi radians, what we end up with is, well, if I did an exact value, 180 times 1.78 is 320.4, and then we'd be dividing by pi. That's the exact value. We'd probably want a nice approximation for that, which would be 101.99. That's 101.99 degrees, approximately. And that's probably what you'd have to plug in this case. So that's how we multiply by 1 to convert from radians to degrees. And obviously we did a multiplication by 1 to convert from degrees to radians just a moment ago. Now, I kind of hinted at this earlier, but our Cartesian coordinate plane can be broken into quadrants. And when we do a full rotation, we start on the x-axis and we rotate through quadrant 1, 2, 3, and 4 and get back to our starting value. And so some nice or interesting angles are the quadrant angles, where our terminal ray is aligned with the x-axis, or whether our terminal ray is aligned with the y-axis, and it can be aligned in the positive direction or the negative direction along either the x or the y-axis. Those quadrant angles are 0 degrees, which right now we could have converted into radians. 0 degrees is the same thing as 0 radians. 90 degrees, and earlier we kind of saw 90 degrees is a quarter turn. So that's what you get when your terminal ray is aligned with the y-axis pointing up. 180 degrees, that's where we have a straight line, our terminal ray and our initial ray form a straight line along the x-axis. By the way, like I've mentioned before, 90 degrees is pi over 2 radians. 180 degrees is pi radians. We kind of already knew that. 270 degrees is where our terminal ray is pointing down along the y-axis. And 360 degrees or 2 pi radians, is where our terminal ray makes a full circular rotation and is aligned exactly with our initial ray. So these are the quadrant angles. And those are important angles. So if we wanted to figure out the degree measures for these, we could. We could also come up with the radian measures. I was kind of talking through that. But I also want to just make you aware of where those radian measures are at, approximate value wise, like pi over 2, pi over um, pi itself, 3 pi over 2, and all of those. So this is kind of just nice stuff to have. So 0 degrees is 0 radians, and there's no rounded measuring there. So 0 radians is the same thing as 0. All right, so rounding. We know that 90 degrees is a quarter of the circular rotation. Remember, a full circular rotation of 360 degrees was 2 pi. And so a quarter of that is going to be 2 pi over 4, which is the same thing as pi over 2. So 90 degrees is pi over 2. A half of a rotation is a pi rotation. And 270 degrees, that's like a 3/4 rotation. That's going to be 3 times 2 pi over 4, which is going to be 3 pi over 2. Now, I just want to make us aware of this. Pi is about 3.14159, right? So if I rounded pi to a couple of decimal places, it'd be about 3.14. That means the radian measure of 90 degrees, while we know the exact value is pi over 2, the rounded value is about 1.57. 2 pi is double 3.14, and that's about 6.28. And then if I go halfway in between pi and 2 pi, or if I take 1.5 times pi, 3 halves times pi, I get about 4.71. So those are the radian measurements of the quadrant angles. Here are the exact radian measurements. Here are the rounded radian measurements of the quadrant angles. Now, 3 other angles of interest are our 30-degree angle, our 45-degree angle, and our 60-degree angle. These are common angles that we're going to use a little bit later on in some of the other sections. So because they're kind of important, I'm going to convert these all into radian measures just so that we have that down. So let's go ahead and convert 30 degrees, 45 degrees, and 60 degrees to radians. Hopefully you see that the reason why we're focusing on this is because 45 is half of 90. And 30 degrees is a third of 90. So these are they give you angles that are 1/3 of the way through the first quadrant, half the way through the first quadrant, and 2/3 of the way through the first quadrant. So I'll do that pretty quick here. 30 degrees, if we're going to multiply that, we multiply times pi over 180. 30 divided by 80 simplifies to a 6. So what we're going to get is pi over 6 radians. Again, if I didn't write the steps, but what I'm doing is I'm taking 30 degrees and then I'm multiplying it times pi over 180 degrees. Okay. So that's what I'm doing, multiplying times pi over 180, getting pi over 6. 45 degrees is pi over 4. I'm not going to write the steps on that one. And then 60 degrees, I could multiply by pi over 180, or I can just realize that because 60 is double 30, I can just double pi over 6. And if you double pi over 6, you get pi over 3. 2 pi over 6 is the same thing as pi over 3. So these are important angles for us in the future. We'll use those quite a lot in the next couple of sections. But I wanted to introduce those now because we're talking about these different quadrant angles. These are also important angles. So now what we're going to do is we're going to use the quadrant angles. One way we can use these quadrant angles is to figure out where the terminal side of our angle is going to be in. So let's start with radian measurements. That's actually a little bit harder. Let's say we have the radian measurement of 7 pi over 4. And we have the radian measurement of 2.11 and the radian measurement of 1.20. And I want to figure out which quadrant these are in. Now, with something like 7 pi over 4, what we could do is we could go back to our quadrants and we could think about where 7 pi over 4 is going to land. You can do that in the exact values if you want, but you can also do that in the approximate values. If you take 7 pi over 4, that becomes 5.497787, so about 5.5. So with a radian measurement of about 5.5, which quadrant would we land in? Because we know the quadrant angles, we can just see which of the quadrant angles put 5.5 between them. So here's what I mean by that. We have 5.5, that's the 7 pi over 4. Notice that that's between the 270 degrees and the 360 degrees, or the 3 pi over 2 and 2 pi over 2. That's between these two numbers. And that means since 270 degrees or 3 pi over 2 points down on the y-axis, let's draw it here. So 270-degree angle points down there, and 2 pi is along the x-axis. That means we're in this quadrant somewhere. Okay, so we're in quadrant 4 in that case. So because 5.5 is between 4.71 and 6.28, I know it's going to be in the terminal side is going to be shooting into quadrant 4. Now I can do that regardless of what my angle is. So my other angle was 2.11 radians. 2.11 is between pi over 2 and pi. So if we think about that, pi over 2 is going straight up along the y-axis. Pi is going to the left along the x-axis. So 2.11 has to have terminal side, right? So Here's my angle. Has to have terminal side in quadrant 2. Now, here's where it gets tricky. It gets a little bit tricky with the negative angles. Negative 1.2, notice that is not here, but what I can tell you is it's going to be between 0 and negative 90 degrees. Since 1.2 is between 0 and 1.57, negative 1.2 is going to be between 0 and negative 1.57. Now, you have to be careful when you draw this or when you think through this, because with negative 90 degrees, we're going to be swinging in the clockwise direction. So negative 1.2 is down here somewhere in quadrant 4. Negative 90 degrees goes this way. Positive 90 degrees goes this way. This would be negative 180. This would be a negative 270. And then this one would be a negative 360. So if I went in the negative direction, that's what happens. So negative 90 straight down, negative 180, negative 270, then negative 360. That's in degrees. If we're in radians, it's negative pi over 2, negative pi, negative 3 pi over 2, and then negative 2 pi in exactly the reverse direction. So we can tell what quadrant we're in pretty efficiently by knowing the angle. That is, we can tell what quadrant our terminal side is in by knowing the angle. Let's do the same with the degrees. So here we have 112 degrees. Well, I actually know that 112 degrees, that's going to be above 90, but under 180. So that's going to be somewhere in quadrant 2. So 112 degrees is going to be in quadrant 2. Negative 105. Well, if I'm going in the negative direction, I'm going clockwise, past negative 90, but not yet to negative 180. So negative 105 is going to be in quadrant 3. Now, here's a little bit of a tricky one. 450. If we go 450 degrees, we've gone more than one time around the circle. We've gone, when we get to one time around the circle, that's 360 degrees. And then we have to go an extra 90 degrees to hit 450. So the 450 degree angle is the same as has the same terminal side as our 90 degree angle. By the way, that terminal side is not in any quadrant because it lies on the y-axis. If ever your terminal ray or terminal side of the angle lies on either the y-axis or the x-axis, then we're not in any quadrant. But 450 degrees goes one whole time around plus an extra 90. So the terminal side, terminal ray of that angle is the same as the terminal side or terminal ray of the 90 degree angle. And angles that do that, two angles that share the same terminal sides, are called coterminal angles. So two angles are coterminal if their terminal sides are the same. In other words, if they're pointing in the same direction. Since 360 degrees is a full rotation, we can keep adding or subtracting 360 degrees to get infinitely many coterminal angles for a given angle. And in the same fashion, I can just keep adding and subtracting 2 pi to give me coterminal angles if I'm measuring in radians. So keep adding 360 over and over and over again. Keep subtracting 360 over and over and over again. Keep adding 2 pi over and over and over again. Keep subtracting 2 pi over and over and over again. Will give you lots of different coterminal angles. For this reason, a lot of times in a lot of scenarios, we may assume that our angles are all between 0 and 2 pi in radian measurement, or that all of our angles are between 0 and 360 in degree measurement. And so it's a nice tool to understand that if I'm have an angle like negative 105 degrees or like 920 degrees, if I want to find the angle that's between 0 and 360 degrees with the same terminal side, in other words, if I want to find the coterminal angle such that my angle is between 0 and 360 to the one that we have here, then all I really need to do is keep adding or subtracting 360 until I get an angle between 0 and 360. Let me show you how to do that. So we want to find the coterminal angle and the coterminal angle that's between 0 and 360. We would simply take 105, negative 105, and I'm going to add 360 to that. When I take negative 105 and then add 360, I get 255. That's between 0 and 360, so I'm done. 255 degrees is a coterminal angle with negative 105 degrees. Now, if I take 920 degrees, instead of adding 360, I'm actually going to have to subtract 360. And I'd actually have to subtract 360 a couple of times because if I subtract 360 once, I'm still not between 0 and 360. Remember, I want a coterminal angle such that we're between our angle, which we call theta, is between 0 and 360 degrees. So if I just did one subtraction of 360, that wouldn't get me there. I'd be at 560. So I'd have to do another subtraction. Sometimes you could just say subtract 360 and then subtract 360 again. Or you could say subtract 2 copies of 360. When you do that, you end up with 200 degrees as the coterminal angle with 920 degrees. And the one we did earlier, 450 degrees, if I subtract 360, that was the same. That was a coterminal with 90 degrees. So that was the previous example. Again, I'm not saying 920 is the same as 200. I'm saying that they are coterminal. So they have the same terminal side. Go ahead and try this technique on your own with radians. Here's a couple of angles measured in radians. We want to find a coterminal angle to the given angle, or angles, such that the coterminal angle has measurement between 0 and 2 pi radians. In a couple of seconds, I'll show you how that's done. Now, the technique that we're going to use here is just adding or subtracting 2 pi over and over and over again until we get an angle between 0 and 2 pi. You can accomplish that in a lot of different ways. So 19 pi over 3 is more than 2 pi because if you think about 19 over 3, that's 6.33 pi. So this is approximately, I'm going to write it down here as about 6.33 times pi. So we need to subtract a few 2 pi copies. In fact, we need to subtract 3 copies of 2 pi in order for that to get between 0 and 2 pi. All right, if I subtract 2 pi, I'd be at 4.33 approximately. If I subtracted a couple of copies, I'd be at 2.33 pi. If I subtract 3 copies, now I'm subtracting 6 pi, and I'm getting about 0.33 pi. Now you can do this again with approximates. You can also do this with specifics. So I shouldn't say 19 pi over 3 is equal to that, but what we're saying is 19 pi over 3. If I subtract 3 copies of 2 pi, what I end up with, let's give the exact version now. That's 19 pi over 3 minus 6 pi. And then 6 pi, if you think about that, if I want an exact answer, 6 pi is 18 over 3, getting common denominators here. So multiply top and bottom by 18, or excuse me, by 3 to get 18 pi over 3. That's the same thing as 6 pi. And that is 1 pi over 3. So 19 pi over 3 is coterminal with pi over 3. Okay, so pi over 3 and 19 pi over 3 are coterminal. And pi over 3, if you remember from earlier, is our 60-degree mark. In the same manner that we did the above example, I'm going to keep adding 2 pi over and over and over. If you add 2 pi, what you're really adding is 10 pi over 5, if you think of it as an improper fraction. If I just add 1 copy of 10 pi over 5, I'm still going to have a negative angle. So we're going to have to add 2 copies of 10 pi over 5. 2 copies of 10 pi over 5 gives me 20 pi over 5. And so negative 18 pi over 5 is going to be coterminal with 2 pi over 5. Again, I did this in the exact way, so I got exact answers. You can also do this in a rounded way if you're looking for approximate answers. Just keep adding 2 pi over and over and over again. In other words, take 18, negative 18 pi over 5. Negative 18 pi over 5 is approximately negative 11.3097, blah, blah, blah. And then I'm going to add to it a copy of 2 pi and then see what my calculator gives me. Right now, it gives me negative 5.02. That's still negative. So then I'm going to add another copy of 2 pi. And all of a sudden, that becomes about 1.2566. which is between 0 and 2 pi, or between 0 and about 6.28. So you could get the approximate value by, just plugging things into your calculator. In any case, whether we're using radian measurements or we're using degree measurements, now I know how to find coterminal angles. So that's the end of this video. In subsequent videos, we will be using these angle measurements along with trig functions. So those will come up in the next few videos.